So in the previous outing, we had calculated the moment of inertia about various axes of some regular bodies like a ring or a rod, as also a disc, as also a cylinder, through various axes. Today I will introduce to you a couple of theorems which are of use to us, and by using these theorems we are able to calculate the moment of inertia about several other axes. Okay. Now, one is called the theorem of perpendicular axis, and the other is called, this is a symbol for parallel, so the theorem of parallel axis. Okay, how to calculate the moment of inertia I. So first of all, I take the theorem of perpendicular axis, which is applicable to laminar bodies, bodies like this. There is a lamina, and for such bodies we will introduce this theorem to you, which says that the moment of inertia of a planar body or lamina about an axis perpendicular to its plane, the axis has to be perpendicular to its plane, is equal to the sum of the moment of inertia of two axes concurrent with the perpendicular axis. This is the perpendicular axis, and suppose I know the moment of inertia about this axis in the plane and another perpendicular to the same axis. Like in the coordinate system XYZ, I have, suppose we know the moment of inertia about the y-axis, we know the moment of inertia about the x-axis, which comprise this within the lamina, and this one is the center of mass or center of gravity of the system. Then we can calculate the moment of inertia about the perpendicular axis, which is going through this center of mass, the center of gravity, etc., whatever you want to say. So I can say in a nutshell that the moment of inertia about the z-axis is equal to the moment of inertia about the x-axis plus that about the y-axis. I tried to draw a rough picture of what is there. This is the lamina. Within the lamina, maybe this is the center of mass of the system, center of gravity of the system, and then I have, this is the z-axis about which the rotation takes place, about which we are asked to calculate the moment of inertia. This is the y-axis and this is the x-axis. And of course, you will say, why not you are taking the x-axis over here? So I can take the x-axis here, then this becomes the y-axis and this becomes the z-axis. If I take the z-axis here, this becomes x-axis, this becomes the y-axis. Okay? So it doesn't matter, but our axis should be in the counterclockwise direction as per the norms of the positive direction, which is called the anti-clockwise motion which occurs. So look here, I take a point P over here. This point P has an associated mass small m. Okay, see, so we take only one particle which is a constituent of the lamina, and we can see that the distance at the point from the x-axis is y, and that is the perpendicular distance from the x-axis is y, and from the y-axis it is equal to x. So this point I can define as xy. This is why what I have done here to clarify the thing to you, and that is I have taken the x-axis, the y-axis and the z-axis. Okay, these are mutually perpendicular axes as I told you, and this point P like here is xy, so this becomes x, this becomes y, and the distance of the point P I have taken here is equal to r. So I could also write an r over here. Okay, and next point is that the moment of inertia about the z-axis over here, because the distance from here to here for the point P is r, therefore it will be equal to mr square. And r square I can write in the following, that r square is equal to x square plus y square. Okay, so taking this, the value of m, etc., I can prove this theorem in the following. So to be able to prove this theorem, I just take a single mass, mr square is the value of Iz defined, and then I sum it over all the points, all the masses like that. So I can write this as equal to sigma for all points. I could write I to 1 to n like I've been doing before, but I can just say that for all the points this is sigma mr square, which I can write as mx square plus y square, because we have found that r square is equal to x square plus y square, because the x direction, the y direction, they are perpendicular to each other, and we are using what we call the Pythagorean theorem. And then I can separate these two quantities, mx square and my square for all point values, and this is by definition, this mx square is by definition Iy, the moment of inertia about the y-axis. The axis is passing through the center of mass and center of gravity, plus Ix, the moment of inertia about y-axis, x-axis, when the x-axis is also passing through O. So this clarifies that in the perpendicular axis theorem, we have these three axes are perpendicular to each other, and we find that Iz is equal to Ix plus Iy. Okay. So the second theorem is the theorem of parallel axes, in which I will explain it to you before I read this out, that if I know, if I can calculate from the basic first principles or otherwise, for a laminar body, which I have just taken here, not to be very regular but irregular, there is a center of gravity, a center of mass of the system, and passing through that I have an axis through the center of mass of the system, which I am designating as Rs. And then I draw a parallel axis PQ parallel to this one, which is separated from this axis by a distance r. And then to prove this theorem, what I have is that I take a mass at this point P, okay, any point I can write this point as P, where the mass m exists, which is at a distance of say x. It could be on this side, it could be on this side, etc., but I am just taking it like that. So from a distance from here, from this axis Rs, the distance of the particle is n. Then I can write, by definition of the moment of inertia, delta I as equal to m into the distance from this axis, and that is r plus x whole square. So let me read the theorem for you. The theorem reads as follows. The moment of inertia of a plane lamina, this is the plane lamina, about any axis in its own plane, is equal to its semi about a parallel axis passing through its center of mass. This is very important. The center of mass at the center of gravity at the center of the body. Okay. Because I'll prove it for the laminar body that this theorem exists only for the axis passing through the center of mass and a parallel axis. So it is about the moment of inertia about the axis which is passing through the center of mass plus and the product of the mass of the lamina. Suppose the mass of the lamina is capital M, okay, and the square of the distance between the two parallel axes. What is that? R, here defined, mr square, plus the moment of inertia about this axis. This is what I am going to show it to you in the following. Okay. So we did see that by definition the moment of inertia of this mass m about this axis turns out to be equal to its mass multiplied by total distance from here to here, which is equal to r plus x whole square, which I am writing again over here for all the points, that the total moment of inertia is the summation for all the points of the mass m into r plus x whole square. Okay. So this I can break. R plus x whole square is equal to r square plus 2rx plus x square. Okay. And then I multiplying with m and taking the summation for all points, I can break it into three parts. Sigma of mr square for all points plus 2 times sigma of mrx that we obtain here plus for all points sigma of mx square. Now we define that sigma of mx square for all these points is the moment of inertia about this axis which is passing through the center of mass of the body by definition. So I write for sigma mr square, I write Ig. Okay, the center of mass is taken to the center of gravity, etc. So I just write it. Symbols don't matter. You can define any symbols of your own, but Ig is a symbol for the moment of inertia of the body through an axis which is passing through its center of mass. Plus this term I am shifting here, sigma mr square plus 2r, I am taking out the sigma of mx because r is the constant. You can see r is not changing. Okay, it is the distance of the axis rs from the axis pq. So if m is the total mass of the lamina, I can write this term over here as sigma all p mr square. R is a constant, I take it out of that. So summation of all the masses for all values of p, all positions p where the masses are situated. So this turns out to be equal to capital M, and therefore the value of this term is equal to mr square. So this must be coming to your mind that the theorem has been proved, because there is one term which is Ig and the other term is which is this, like this. So mr square plus Ig plus mr square. So Ig plus mr square, Ig plus mr square, where r is the separation between the two axes. So what follows, what comes to our mind is that we should be able to prove that this value here 2r sigma of mx, this must be shown in the following argument, that this is equal to 0. If it is equal to 0, and I will show it to you that this term turns out to be equal to 0, then the value of the moment of inertia will turn out to be equal to Ig plus mr square. So third term that was there, I have to show that this is equal to 0. How do I do that? The axis is passing through the center of mass, and if I put a wedge under RS over here, under RS, and I am able to balance the body on that wedge on a kind of a sharp and long knife edge. If I keep the body over there and that is passing there, then what we find that because the RS passes through O, RS is the axis which is the original axis for which the center of mass is known and the moment of inertia is known to us. It passes through the center of mass. The lamina will balance a wedge immediately under RS. What does that mean? It means that the algebraic sum, what is an algebraic sum? The quantities when they are plus and minus both, then the sum is called an algebraic sum. Algebraic sum of the moments of the weights. What is this moment? This moment is moment of a weight. Weight is basically what we call a force. The force multiplied by the distance where the force is acting, okay, from the axis, this gives us the torque tau. And the torque is, the torque for different masses will be clockwise or anti-clockwise. The torque will be like that. So, when there is a balance, that means that the net torque that we calculate for this thing are the net moment of the weights of its individual mass particles about this center of mass wedge, that is going to be equal to 0. Which means that the weight here is mg, and to calculate the moment I'm not using the vector definition, that's why I'm using the star as a multiplier over here. So mg into x, that will turn out to be equal to 0, which I can write. I can take g out of it, and for the summation for all the point masses which constitute the laminar body, this is mx is equal to 0. Okay, so if I put it there, then r is a constant and this is equal to 0. So the third term in the equation that we had, that turns out to be equal to 0, and therefore the moment of inertia about the axis PQ, which is parallel to the axis RS, will be equal to the moment of inertia about the axis RS plus the mass of the lamina multiplied by the distance r of the axis from there, which I can also write in the following form, that I is equal to ICM. For G I can write center of mass here plus mr square. Now in the following I will show you a couple of applications of these theorems which we can apply and calculate. Some things we have done before also using the integral calculus. Now we are going to use these theorems to obtain those results. So we want to apply the theorem, parallel axis theorem. In the case this is given that, and we know that I have calculated it for us before, the moment of inertia of a thin rod of mass m and length capital L about an axis perpendicular to its length and passing through its center of mass is this axis we are talking about, is ml square by 12, which is the result which we remember from our calculations, okay, before. From the first principles we took a small mass of a length dx, multiplying it with mass per unit length and then integrating it from minus L by 2 to L by 2, and we found that it is equal to ml square by 12. But now we are just making an application of the theorem, and I write it as I is equal to moment of inertia about the new axis is equal to the moment of inertia about the defined axis which is passing through the center of mass plus the mass of the rod multiplied by r square, where r is the distance between the two axes here. This is r and it turns out to be equal to L by 2. Okay, so in the application it's very simple. Scribbling half a minute time for you, ml square by 12 plus ml square by L by 2 whole square, which is L square by 4. So I am writing it ml square 1 upon 12 plus 1 upon 4. Okay, and just I am making the two denominators the same, 12 here and 12 here, so this turns out to be equal to 3, 1 plus 3, that is 4, 4 divided by 12, and that turns out to be equal to ml square over 3. Okay, now it's not only this case that one of the ends, but I can have any axis which is distant r from here. This is distance r from here, and about this axis also, if we ask you to calculate the moment of inertia, then you can use the theorem, use the value of r whatsoever it is in terms of L, and you obtain the results. So this is one very simple thing that we have done. I'll take up another example of ring. So there is a very simple exercise that we want to do just now to calculate the moment of inertia of a thin ring about a tangent to the ring. Okay, the tangent is in the plane of this thin ring of radius r, and naturally the distance from here to here to of the diameter to the tangent is equal to r. This diametrical axis is passing through the center of mass, and the value we know about this is mr square by 2. Okay, so I just substitute in this relation that I will be equal to the I about the diameter, the axis that we know about, we are familiar with, plus mr square. Now r is equal to capital R, therefore I can write this mr square by 2 plus mr square is 3 by 2 mr square. Incidentally, we know that for a ring, the moment of inertia about an axis which is passing through its center of mass and perpendicular to it is equal to mr square. And then I can just choose any two diameters which are perpendicular to each other and which are passing through its center of mass, for example this diameter and this diameter, and they are equal in their face value, and therefore I can say that the moment of inertia about this diameter for the moment of inertia plus the moment of inertia about this diameter is equal to the moment of inertia about the perpendicular axis. So mr square is equal to something plus something, and that is equal. So the value of the moment of inertia about this any diameter turns out to be equal to mr square divided by 2. So this is how we have been able to calculate. Many other things can be given to you. The moment of inertia of that geometrical body is known to us, the planar body. Then of course we can apply the two theorems judiciously, okay, and obtain the results, calculate the results very, very fast. You must know how to scribble and obtain the results from not so many formulae but some formulae like this. Okay, so that way we have I now ask you to do more examples so that you are more versed in the calculations of moment of inertia of various bodies. But I will just ask you that please understand this UQVA. That is, you question us, you make queries, and we'll try to answer them in the comment section. That's one thing. The second thing is, I'm not being professional, but for your sake I'm going to tell you that please subscribe the channel, and that will be to your benefit, because whenever the new lecture or class comes up, it will be notified to you. You know that. And now the next item, we have done with the moment of inertia. We have done with the calculation of moment of inertia, definition of moment of inertia, the two theorems associated with that, and we have applied the two theorems in some situations. Now next item that we take up in the next lecture is the kinematics of rotational motion, where I will equate things like mass, moment of inertia, omega v, alpha a, torque, force, etc., etc. The counterparts in the translatory motion and the rotational motion we'll discuss. It's a bit tricky. We'll do that in the next couple of lectures. Thank you very much.